Okay, in this little video I'm going to go through the exercise that I set to you a couple of weeks back. It's on page 168 of your EGM 90 Advanced Aerodynamics lecture notes. It's exercise 3 where I ask you to have a go at adapting the Prandtl-Glauert rule, which we came across back in section 3.4.2, to estimate, to create an estimate for the compressible pressure coefficient and critical pressure coefficient in the context of a swept wing, because that was something we considered as being important in the section we've just completed, where we've looked at supersonic aerodynamics in the context of the Bloodhound supersonic car. Of course, the Bloodhound supersonic car has winglets at the front and the back, which are swept for this very reason. So the first thing we need to do is assume that our swept wing is actually infinitely long, because of course the Prandtl-Glauert rules, as we developed them, were 2D pressure coefficients. So they assumed that you've got 2D flow or an infinitely long 3D wing. We're going to ignore the non-2D effects that result from having an actual wing root here, or an actual wing tip here. So we're assuming effectively that the isobars, the lines of constant pressure, run parallel to the leading edge of the wing in this direction here. Of course, this means that locally our velocity vector normal to the wing looks like this, if this is our actual velocity vector. And in the free stream we can say that that u swept, our effective normal free stream, relative to u infinity, the actual free stream. So the effective free stream, the normal free stream, u swept, is equal to u infinity cos lambda, where lambda is the sweep angle of our wing. And we're also going to make this assumption here that p minus p infinity, so the deviation of pressure from its ambient condition in the free stream for this swept wing at u infinity, of course, a swept wing is, by definition, has a 3D geometry. There's no such thing as a 2D swept wing. But we're going to assume that our p minus p infinity values that run that have isobars parallel to the leading edge. So p minus p infinity for swept wing at u infinity is equal to p minus p infinity for a 2D wing, because we're going to apply this to the Prandtl-Glauert rule, at u swept. Okay, so at a free stream condition of u swept. So once we've made that assumption, we can note a few things. So here's our basic definition of CP. This is the thing that we're going to try and develop. So CP for our swept wing is simply p minus p infinity, the actual p minus p infinity on the wing, over a half rho the actual u infinity squared. That is actually the definition of pressure coefficient. Nothing clever there. But we're going to assume that Cp, the 2D pressure coefficient, again will be p minus p infinity over half rho u swept squared. Now that follows directly from this assumption that we've made above, that p minus p infinity for a swept wing at u infinity is equal to p minus p infinity for a 2D wing at u swept. And we know that we can sub in for u swept is a half rho, really these should be rho infinities, this should be a rho infinity, half rho infinity u swept, and this is u infinity squared cos squared lambda, from our definition up at the top, up there. Now just comparing those two expressions, obviously this implies that Cp for a swept wing is equal to Cp for a 2D wing times cos squared of lambda. So this is the first thing that we can note, almost just from pure geometry and definitions of pressure coefficients. Now, if you remember, the Prandtl-Glauert similarity rules had a similarity factors, and one of these that was important was beta, and so this comes directly from the theory in section 3.4.2. So the Prandtl-Glauert similarity factor beta was equal to the square root of 1 minus m infinity squared, and we derived the Prandtl-Glauert rule and showed that this similarity factor beta was important. Now the implication of having a swept wing is simply that beta for a swept wing, we have to adapt m infinity and make m infinity cos lambda. So beta now becomes, we should call this beta for a swept wing, is 1 minus cos squared lambda and we can just sub those two things in to the Prandtl-Glauert rule that we had back in section 3.4.2, which, I'm just going to look this up, is equation this is equation 3.67 in your notes. So equation 3.67, which is on page 102 of your notes, becomes Cp at a free stream Mach number of m infinity with thickness factor tau and aspect ratio AR, but now for a swept wing, because of the above, now becomes cos squared lambda over the square root of 1 minus cos squared lambda m infinity squared. So this is the factor that we multiply by the incompressible pressure coefficient, so the Cp at effectively Mach 0 or incompressible, that is what we're really saying there, the incompressible pressure coefficient with the same value of tau but beta times a r. So this is the Prandtl-Glauert rule adapted for a swept wing. Okay, and then in section 3.4.4 we talked about critical Mach number, and before the critical Mach number we derived an expression for the critical pressure coefficient, which is the other thing I've asked you to derive the swept wing equivalent for. So equation 3.76 we derived this relationship. So this is from let me just check that's coming from the right place. Yeah, 3.76. we had this. So Cp, once again, just starting with the basic definition, P minus P infinity over half rho infinity U infinity squared. And we showed that this is equal to 2 over gamma m infinity squared P over P infinity minus 1 and then substituting into this isentropic relationships, we turn that into 2 over gamma m infinity squared one plus half gamma minus 1 m squared over 1 plus half gamma minus 1 m infinity squared, all raised to the gamma over 1 minus gamma minus 1. And what's important to note is when we derived this, what we've got here is this term, which is essentially related to the normalization by dynamic pressure. So this term here basically comes from this part. And the bit of this that will be affected by the sweep is this term here. So our deviation of pressure from P at infinity, which is represented by this term here. So this term here is the term that's going to be affected by sweep. So we leave this term on its own. That just stays as it is in the swept equivalent of Cp. But we need to adapt that second term inside the curly brackets. So Cp for a swept wing, and again it's just a case of adapting that m term to be the normal Mach number or normal free stream Mach number. So this becomes 2 over gamma m infinity squared, and the only subtlety here is in recognizing where the different bits of this equation come from, and that first term is basically the normalization with free stream dynamic pressure. Free stream dynamic pressure doesn't change as a result of sweeping the wing. What changes is the actual P minus P infinity that you experience on the surface of the wing. So this becomes 1 plus a half gamma minus 1. Of course, these are all just constants, and then we have to substitute, instead of m squared, now we've got cos squared lambda m squared over 1 plus gamma minus 1 cos squared lambda m infinity squared. And of course the critical pressure coefficient is the pressure coefficient that occurs when the local Mach number first reaches sonic, when it first reaches 1. Now in the case of a swept wing, the critical pressure coefficient will occur when the local normal Mach number first hits 1. So when this term here goes to 1. So when that is 1, you have the critical pressure coefficient. So if we simply substitute in for this term here as 1, we can say that Cp swept star, where star now indicates that this is the critical pressure coefficient, is 2 over gamma m infinity squared 1 plus a half gamma minus 1, and then that multiplies by 1 over 1 plus And of course we can tidy up the top of that if we want. We could write this as that simply boils down to, I think, just gamma plus 1, doesn't it? Yeah, gamma plus 1 over... Yeah, then we can take out a factor of 2, so we'll end up with a 2 at the bottom plus gamma minus 1 cos squared gamma m infinity squared all to the gamma over gamma minus 1 minus 1. So there it is, Cp for the critical Cp for a swept wing looks like this relationship here.